On the morning of September 1st, 1859, the world was on the brink of a major technological revolution that would change human communication forever. Under the clear skies of Red Hill, England, amateur astronomer Richard Carrington adjusted his brass telescope, projecting a detailed image of the sun onto a white screen. He was cataloging an unusually large cluster of sunspots, dark patches of intense magnetic activity on the solar surface. Suddenly, at 11:18 a.m., Carrington witnessed something never recorded before. Two patches of brilliant white light erupted directly within the sunspot cluster. The flash was so intense it outshone the solar disk itself. Believing a stray beam of light had entered his equipment, Carrington checked his instruments, but the light was real. It was the first recorded solar flare in human history, a colossal release of energy equivalent to billions of megatons of TNT. What Carrington did not know was that this flash was only the trigger. A massive bubble of superheated plasma, a coronal mass ejection, had just been launched directly toward Earth. Traveling at over 4 million miles per hour, this charged cloud crossed the 93 million mile gulf of space in just 17 and a half hours, a crossing that typically takes several days. When it collided with Earth's magnetic shield, the impact was violent. By the early hours of September 2, the night sky across the planet transformed into a surreal show of crimson and emerald. Auroras, usually confined to the polar regions, flared up across the globe. People in Cuba, Jamaica, and Hawaii looked up to see the northern lights dancing overhead. In the Rocky Mountains, the sky was so bright that miners woke up and began preparing breakfast, thinking it was dawn. But the beauty of the lights hid a destructive power. The electrical surge was so intense that the newly established telegraph network, the internet of the 19th century, went completely haywire. Electric currents flooded the lines. Operators reported sparks jumping from their equipment, setting fires to telegraph stations. Some systems continued to send and receive messages even after operators disconnected the batteries. Powered entirely by the electricity flowing through the ground, it was a stark warning of the sun's power. If you want to understand the terrifying physical limits of our star and how to prepare for the inevitable Carrington Event 2.0, subscribe to Deep Space Signal. Let's decode the universe together. The Carrington Event of 1859 proved that our planet is not isolated. We live inside the extended atmosphere of an active star. While our ancestors watched the skies in wonder, their simple technology saved them from total disaster. Today, we have built a global civilization completely dependent on electricity, wireless signals, and microchips. A repeat of the Carrington Event would not just spark telegraph wires, it could bring our entire modern world to a sudden standstill. To understand the physical forces that caused this storm, we must examine the delicate wiring of the telegraph networks and how they became accidental antennas for the sun's fury. This historical milestone teaches us that space weather is not a distant concern, but a repeating reality that we must prepare for. Our survival depends on our ability to shield our grids before the next great solar storm hits. To comprehend the scale of the 1859 solar storm, one must look at the bizarre experiences of telegraph operators on that fateful September morning. As the geomagnetic storm reached its peak, telegraph lines across Europe and North America became completely unusable. The air seemed charged with static electricity, and the machines began operating erratically. In Boston, an operator named George Prescott noticed that the current on the line was incredibly strong. He decided to disconnect the heavy chemical batteries, which consisted of large glass jars filled with copper sulfate and zinc, that normally powered the telegraph system. To his amazement, the machines did not die. Prescott and his colleague in Portland, Maine, discovered they could converse easily using only the auroral current. For over 2 hours, they sent messages back and forth across a distance of 110 miles, without any battery power. The Earth itself had become the battery. This phenomenon was caused by geomagnetically induced currents. As the massive cloud of solar plasma collided with Earth's magnetic field, it caused the field to shake and compress violently. A changing magnetic field near a conductor, in this case, thousands of miles of copper telegraph wires stretched across the countryside, induces an electrical current. The longer the wire, the more current it collects. These currents did not just travel through the wires, they surged through the ground itself, seeking the path of least resistance. The telegraph lines acted as giant antennas, capturing the energy of the solar storm and channeling it directly into the receiving equipment. While some operators managed to use this current, Others were not so lucky. In many offices, the currents were too strong to handle. Sparks flew from the key transmitters, igniting the paper tape used to record messages. Some operators received severe electrical shocks when they touched the metal keys. Beyond the telegraph offices, the physical signs of the storm were visible to everyone. The auroras were so bright that they cast distinct shadows on the ground in regions as far south as Rome, San Salvador, and Santiago. People looked up in disbelief as the night sky burned with deep red and violet colors, thinking their cities were on fire. The sheer energy involved in this event was staggering. Scientists estimate that the Carrington Event was twice as powerful as any solar storm recorded in the space age. It was a global event that shook the magnetosphere to its core. The lesson of 1859 is that when a geomagnetic storm hits, long metal conductors are the first things to fail. In the 19th century, these conductors were simple telegraph wires. In the 21st century, they are the massive high-voltage transmission lines that span continents and feed our cities. The fire that burned the telegraph wires in 1859 was a preview of a much larger danger. To understand how such an event begins, we must look at the source of this power. We must look at the sun itself and the complex magnetic engine that drives these extreme storms. This solar engine operates on a scale that dwarfs any human creation, turning simple magnetic fields into weapons of global disruption. To understand the threat of a modern Carrington event, we must look at the physics of the sun. Our star is not a solid object. It is a giant sphere of hot plasma, a gas of charged particles. Because it is fluid, the sun rotates at different speeds. The equator completes a rotation in about 25 days, while the polar regions take up to 35 days. This differential rotation creates a massive dynamo effect. The magnetic field lines inside the sun are stretched, twisted, and wrapped around the star like tight rubber bands. Over time, these magnetic lines become extremely distorted. Under the intense heat of the solar interior, bubbles of plasma rise, carrying the twisted magnetic fields to the surface. Where these fields break through the solar crust, they inhibit the upward convection of heat. This creates cooler, darker regions on the surface that we see as sunspots. These sunspots are not calm areas. They are highly active magnetic zones where lines of force are packed tightly together, storing immense amounts of potential energy. As the sun's rotation continues to twist these fields, the magnetic loops stretch higher into the solar atmosphere, forming gigantic arches of plasma. Eventually, the tension becomes unsustainable. The magnetic field lines twist so tightly that they cross and snap. In a process called magnetic reconnection, the field lines rapidly realign, releasing the stored energy in a sudden violent explosion. This is a solar flare, a burst of intense electromagnetic radiation that travels at the speed of light. It releases energy equivalent to millions of hydrogen bombs detonating simultaneously. But the flare is only part of the story. The violent snapping of the magnetic fields often launches a coronal mass ejection. This is a colossal bubble of solar plasma containing billions of tons of electrons and protons, bound by strong magnetic fields. While the light from the flare reaches Earth in just 8 minutes, the plasma cloud travels much slower, taking anywhere from 15 hours to several days to cross the void. When this cloud is directed toward Earth, it acts as a massive magnetic hammer. It carries its own magnetic field, and if that field aligns against the magnetic shield of our planet, the two will merge. This connection allows the solar plasma to transfer its energy directly into Earth's space environment. The sun is a repeating engine of these eruptions, operating on an 11-year solar cycle. At the peak of this cycle, known as solar maximum, the sun can produce multiple large coronal mass ejections every day. Most of these miss our planet, expanding harmlessly into the empty space of the solar system. But occasionally, orbital paths align perfectly, placing Earth directly in the path of a solar superstorm. The danger is not a matter of if it will happen, but when the next major eruption will target us. This was the case in the summer of 2012, when a massive solar storm narrowly missed our planet by a very thin margin of orbital timing. If that storm had hit us, our entire global network could have been disabled. Our safety systems are designed for minor solar fluctuations, but they are completely inadequate for the extreme events that our star is capable of producing at any moment. On July 23, 2012, the sun unleashed a storm of historic proportions. A massive coronal mass ejection erupted from the solar surface, throwing billions of tons of magnetized plasma into space. In terms of size, speed, and magnetic intensity, This storm was comparable to the Carrington Event of 1859. It was the most powerful solar storm recorded in over a century. Yet, as this colossal cloud of plasma tore through the solar system, the citizens of Earth remained completely unaware. We did not see auroras, and our power grids remained stable. This was not because our technology was shielded, but because we were incredibly lucky. Earth missed a direct hit by only 9 days. In its annual orbit around the Sun, our planet had passed the point of eruption just over a week earlier. The plasma cloud swept through the empty space of Earth's orbit, crossing the exact path where our planet had been. If the eruption had occurred 9 days earlier, a Carrington Event 2.0 would have struck us head-on, changing our history in an instant. Although the storm missed Earth, it did not miss our technology. The eruption was directed toward a NASA satellite called Stereo A. This solar observatory was positioned in orbit ahead of Earth, designed to monitor space weather and solar activity. When the plasma cloud hit Stereo A, the satellite's instruments recorded the impact in real time. The data was shocking. The solar wind speed spiked to over 2,000 kilometers per second, which is 3 times faster than a typical coronal mass ejection, translating to over 4.5 million miles per hour. The magnetic field strength of the storm was extremely high, registering values that stunned scientists on Earth. Researchers analyzing the data later realized that this was a perfect solar superstorm. If it had hit Earth, it would have compressed our magnetosphere to a fraction of its normal size, sending powerful electrical currents through our power grids. A study by the National Academy of Sciences estimated that the economic cost of a direct hit would have exceeded $2 trillion in the first year alone. The damage to high-voltage transformers would have left major parts of the world without electricity for months or even years, as these devices cannot be replaced quickly. Without power, water systems, food refrigeration, and medical services would have collapsed, causing unprecedented social instability. The 2012 near miss was a silent warning. It demonstrated that the Carrington Event was not a unique historical anomaly, but a repeating hazard. The Sun is a volatile star, and we are sailing through a shooting gallery of magnetic storms. Our modern society has built its entire infrastructure on the assumption that the sky will always remain quiet. But the data from Stereo A prove that this quiet is temporary. We are currently living on borrowed time, and the next storm is already building in the solar furnace. To understand what happens when a storm does not miss, we must look at how our planet's magnetic shield reacts. We must examine the physics of the magnetosphere, our first and only line of defense against the solar wind. To understand how vulnerable our modern world is, we must first look at the invisible shield that protects us every single second. Our planet is constantly bathed in a stream of charged particles flowing from the Sun, known as the solar wind. This solar wind, composed of high-energy protons, electrons, and helium nuclei, travels at millions of miles per hour, carrying magnetic fields and radiation that would easily strip away our atmosphere and sterilize the surface of the Earth if left unchecked. Fortunately, deep beneath our feet, a powerful defense mechanism is at work. The Earth's outer core, a churning ocean of liquid iron and nickel, acts as a massive electromagnetic dynamo. This motion generates a vast magnetic field that extends tens of thousands of miles into space, creating a protective bubble known as the magnetosphere. The magnetosphere is not a perfect sphere. Instead, it is shaped like a teardrop. The side facing the Sun is compressed by the pressure of the solar wind, forming a boundary called the bow shock, while the opposite side is stretched out into a long magnetic tail that reaches far past the orbit of the Moon. Within this magnetic bubble lie the Van Allen radiation belts, 2 donut-shaped zones where energetic particles from the Sun are trapped and deflected away from the planet. Under normal conditions, this invisible shield works perfectly, directing most of the solar radiation safely around us and funneling only a small portion toward the polar regions where they react with our atmosphere to create the beautiful auroras. Without this constant shielding, modern satellite navigation, space travel, and even surface life would be completely impossible. But the Sun is not always calm. During a major solar event, such as a coronal mass ejection, billions of tons of solar plasma are launched into space. When this massive cloud of charged particles collides with our magnetic shield, it does not just slide past. Instead, it delivers a massive physical blow. The incoming solar magnetic field can align opposite to Earth's magnetic field, causing a process called magnetic reconnection. This acts like a door opening in our planetary defenses, allowing immense amounts of solar energy to pour directly into the magnetosphere. The impact is violent. The side of the magnetosphere facing the Sun is compressed from its usual distance of about 10 Earth radii down to a fraction of that size, exposing our highest satellites to the raw fury of the solar wind. The magnetic tail is stretched to its breaking point until it snaps back, sending waves of intense electromagnetic energy rushing toward the Earth. This is the beginning of a geomagnetic storm, a global disturbance that shakes the very foundations of our planet's magnetic environment. In the past, these storms passed largely unnoticed by humans, causing nothing more than spectacular light displays in the night sky. Today, however, our entire civilization runs on electrical currents, and a disruption of this shield is no longer just a scientific curiosity. It is a direct threat to the systems that keep our societies running, exposing our deep reliance on technological infrastructure that was never built to withstand a cosmic onslaught. If an extreme coronal mass ejection were launched directly at Earth today, the first warning sign would arrive in just over 8 minutes. Traveling at the speed of light, an intense flash of electromagnetic radiation in the form of X-rays and extreme ultraviolet light would strike our atmosphere. This initial wave is the solar flare. It immediately ionizes the upper layers of the atmosphere, particularly the ionosphere, which is the region we rely on to bounce high-frequency radio signals across the globe. In an instant, international flights lose contact with air traffic control over the oceans, and maritime navigation systems go silent. This is the global radio blackout, severing the communications that bind our modern world together. At the same time, this sudden atmospheric ionization disrupts the signals traveling between Earth and our global positioning satellites. GPS signals, which must pass through the ionosphere with microsecond precision, are bent and scattered. For a few hours, civilian navigation becomes wildly inaccurate, and eventually, the system fails entirely. This means automated shipping, military operations, and precision farming are suddenly blinded. Commercial aviation is grounded as planes can no longer verify their exact positions in the sky. But the threat to our orbital infrastructure is only beginning. While the light-speed radiation causes immediate disruptions, a wave of highly energetic solar protons moving slightly slower arrives within hours. This solar proton event is a physical bombardment. As these subatomic particles collide with satellites in high Earth orbit, they penetrate the delicate electronic shielding. They cause phantom commands in computer memories, corrupt vital data, and permanently degrade solar panels. Satellites start to spin out of control, and operators lose their ability to send commands to correct them. The outer shells of these satellites build up massive electrostatic charges, leading to internal arcs that fry critical wiring. Meanwhile, the raw energy deposited by the solar flare heats the Earth's upper atmosphere. As the gases in the thermosphere absorb this energy, they expand outward, stretching the atmosphere further into space. This sudden expansion creates an unexpected hazard for satellites in low Earth orbit. The density of the gas in their orbital path increases dramatically, creating atmospheric drag. This drag acts like a brake, slowing the satellites down. Without active propulsion to boost their altitude, hundreds of low Earth orbit satellites, including communications networks, begin a slow and irreversible decay, falling toward the planet. Within the first 12 hours of the event, the sky is already filled with silent, failing machinery. Our orbital eyes are blinded, and our long-range communications are severed. Even if backup systems attempt to route data through terrestrial lines, the scale of the outage renders these efforts useless, leaving modern society in complete informational isolation. The global network we spend billions of dollars to build is reduced to a constellation of drifting metal. Yet, the most dangerous part of the storm has not even arrived. The actual mass of the coronal ejection, a billion-ton cloud of magnetized plasma, is still traveling across the vacuum of space, heading directly toward us at millions of miles per hour. Between 15 and 24 hours after the initial solar flare, the main body of the coronal mass ejection finally reaches Earth. This is a colossal cloud of magnetized plasma, consisting of billions of tons of protons and electrons, traveling at millions of miles per hour. As this ocean of charged particles slams into our magnetic storm, the Earth's magnetic field lines are compressed, warped, and violently shaken. As these magnetic lines fluctuate rapidly above us, They induce powerful electrical currents in the ground beneath our feet. This is Faraday's law of induction operating on a planetary scale. These currents, known as geomagnetically induced currents, travel through the Earth's crust. Under normal circumstances, the ground is a poor conductor of electricity, meaning these currents search for the path of least resistance. That path is our electrical grid. The modern power grid is a giant web of metal wires stretching across continents and deeply grounded into the Earth at thousands of substations. The geomagnetically induced currents enter our electrical systems through these ground connections, surging upward into high-voltage transmission lines. In areas with highly resistive rock, like granite, the currents are forced entirely into the power lines, creating massive, unchecked electrical loops. This electrical surge is unlike anything our grid was designed to handle. Our systems run on alternating current, which reverses direction dozens of times per second. Ground currents, however, are essentially direct current. When this direct current enters the massive extra high voltage transformers that regulate the grid, it causes a physical phenomenon called magnetic saturation. The magnetic field inside the transformer's iron core becomes overwhelmed, causing the transformer to operate wildly outside its safety margins. These giant machines, which step up voltage to hundreds of thousands of volts for long-distance travel, are completely defenseless against this low-frequency surge. The consequences are immediate and catastrophic. Instead of cleanly stepping down voltage, the transformer begins to draw massive amounts of reactive power from the grid. This causes the internal temperature of the transformer to skyrocket within minutes. The insulating oil surrounding the copper windings begins to boil, releasing flammable gases. Deep inside the sealed multi-ton steel tank, the copper coils themselves begin to melt and fuse together. The internal pressure builds until the tank ruptures, leaking burning oil and triggering massive explosions at key substations. Extra high voltage transformers are the critical pressure points of our entire energy infrastructure. They cannot be easily bypassed, and they cannot be quickly repaired. These extra high voltage units cannot be mass produced. They are hand assembled and must be individually transported on specialized rail cars, meaning that replacing even a fraction of them is a logistics nightmare. If a transformer melts, the portion of the grid it supports goes dark instantly. As these critical components begin to burn out one by one across the continent, the safety systems designed to protect the grid are overwhelmed. The stage is set for a massive cascading failure that will sweep across the network faster than human operators can react, plunging entire nations into darkness. When key transformers begin to fail and melt, the electrical grid does not just fail in isolated patches. The modern power grid is a highly integrated machine, designed to share power across massive distances, to keep supply and demand in a perfect, delicate balance. When a major transformer burns out, the power it was carrying must go somewhere else. It is instantly diverted to neighboring lines, overloading them almost immediately. To protect themselves from melting under this sudden stress, these neighboring lines use automated safety switches called circuit breakers, which trip and shut down the lines. This safety feature is what triggers the disaster. When one line shuts down, the excess power is redirected to the remaining lines, overloading them in turn. This starts a rapid chain reaction, a domino effect known as a cascading failure. Within milliseconds, automatic protection systems shut down generator after generator to prevent them from tearing themselves apart. As the generators go offline, the balance of the grid is completely destroyed. The frequency of the electrical current, which must remain at exactly 60 Hz in North America, fluctuates wildly, causing other power plants to disconnect automatically. Voltage drops across the entire network, and the grid begins to tear itself to pieces. Human operators in control centers are completely powerless to stop this cascade. The speed of the collapse is measured in fractions of a second, far faster than any human can read a warning screen, let alone press a button to isolate the problem. In past blackouts, operators had minutes to adjust power generation or cut off specific cities to save the rest of the grid. During a Carrington-class geomagnetic storm, the overload is so widespread and the ground currents are so intense that the entire system collapses automatically. Within a few hours, the blackout spreads across entire borders, ignoring national boundaries. From the air, the transition is terrifying. Vast cities, home to millions of people, go dark in an instant, their lights blinking out like candles in a gust of wind. The hum of electricity that has defined human life for over a century simply stops. There is no internet, no running water, and no communications. As water pumps lose pressure and fuel depots run out of backup electricity, the very foundations of urban survival begin to crumble in silence. The flow of information, fuel, and food, all of which depend on a constant supply of electricity, is cut off. This is the instant end of modern convenience. We have built our entire civilization on the assumption that electricity is a permanent, infinite resource that will always flow when we flip a switch. We have forgotten that this flow depends on a fragile network of metal and wires, protected by a thin magnetic shield that is currently being battered by a hostile star. As the last regional grids go dark, billions of people are left in pitch darkness, completely unaware that the world they knew just a few hours ago has ceased to exist. When the power grid fails on a continental scale, an invisible countdown begins. Modern cities are not designed to be self-sufficient. They are complex life support systems kept alive by a continuous, fragile flow of electricity, fuel, and information. Within the first 24 hours of a global blackout caused by an extreme coronal mass ejection, the thin veneer of technological civilization starts to fracture. The systems we trust with our lives are deeply interdependent, and the failure of one triggers the immediate collapse of another. The first critical failure occurs in our municipal water systems. Most people assume that water flows from their taps purely because of gravity. But in reality, modern water networks rely on massive electrical pumps to treat, filter, and transport clean water to millions of homes and businesses. When the high-voltage transmission lines fail, these pumps fall silent. Within hours, water pressure drops to zero, taps run dry, and the water remaining in the municipal pipelines becomes stagnant. Without running water, modern sanitation systems cease to function. Millions of people in high-rise apartments and dense suburban developments suddenly find themselves, without the most basic necessity for human life, creating an immediate public health emergency. Simultaneously, the fuel distribution network gridlocks. Gasoline and diesel do not flow from underground storage tanks by themselves. They require electric pumps at every service station. With the electrical grid offline, these pumps are completely useless. Emergency generators at gas stations, if they exist at all, can only run for a few hours before exhausting their local supply. This brings transport and commerce to a sudden, grinding halt. Delivery trucks cannot refuel, which means the logistics lines that feed our cities are severed. Supermarkets operate on a strict just-in-time delivery model, holding only enough inventory to feed their local communities for roughly 48 hours. As panic spreads and deliveries stop, store shelves are stripped bare in a matter of hours. The food supply chain does not merely slow down, it vanishes. At the same time, the communication network collapses. Mobile phone towers are equipped with backup batteries, but these are designed to handle short-term local outages lasting only 2 to 4 hours. As these batteries drain, cellular coverage drops segment by segment, creating massive dead zones. The internet, which we treat as a permanent utility, disappears as servers lose power and underwater fiber optic repeaters fail. People are left in complete isolation, unable to contact family, call for help, or receive official information. The silence is absolute. Without coordination, local emergency services are blind. Police, fire, and medical teams cannot receive calls. And even if they could, their emergency vehicles would soon run out of fuel. By the end of the third day, the silent crisis has transformed into a chaotic fight for survival. The complex web of global logistics that keeps 8 billion people alive has snapped, leaving every community completely on its own in the dark. This is not a temporary inconvenience. It is a systemic shutdown. Without fuel, water, or communications, the basic functions of local government dissolve, leaving citizens to rely entirely on their own immediate resources. If a Carrington-class solar storm struck the modern world today, the initial blackout would only be the beginning of a cascading global emergency. The immediate loss of electricity would trigger a series of failures that would quickly overwhelm our emergency services and critical infrastructure. The primary threat is not the lack of light. It is the total breakdown of the complex invisible networks that keep modern society functioning. Within minutes of the geomagnetic impact, the global financial system would freeze. Modern commerce relies entirely on secure, real-time communication between servers. Without internet connectivity or power, credit card networks, electronic banking, and stock exchanges would instantly go offline. ATMs would be useless, and digital transactions would cease. In a society that has largely abandoned cash, People would find themselves unable to buy food, fuel, or medicine even if supplies were available. Commerce would collapse into a primitive bartering system overnight. Simultaneously, the healthcare system would face an unprecedented crisis. While hospitals are equipped with diesel generators to keep life support systems and critical equipment running during power failures, these systems are only designed for short-term emergencies. Most hospitals carry only enough diesel to run their generators for 3 to 5 days. Once the fuel runs out, and with no way to pump or transport more, the generators would fall silent. Intensive care units, neonatal wards, and operating rooms would lose power, resulting in an immediate loss of life. Perhaps the most terrifying threat, however, lies in the nuclear sector. Worldwide, there are over 400 operational nuclear power reactors. When the external electrical grid collapses, a nuclear power plant automatically shuts down its fission reaction. However, the radioactive fuel rods inside the core and the spent fuel pools remain extremely hot and must be continuously cooled by circulating water. To do this, the plants rely on the electrical grid. When the grid fails, emergency diesel generators automatically start up to power the cooling pumps. Just like hospitals, these nuclear facilities only have a limited supply of fuel, typically lasting for about 1 to 2 weeks. If the grid is not restored and fuel deliveries are impossible due to the transportation collapse, these generators will run out of diesel. Without active cooling, the water in the spent fuel pools will boil away and the reactor cores will begin to melt. This would lead to catastrophic meltdowns and containment breaches at multiple facilities, simultaneously releasing radioactive material into the atmosphere. A Carrington Event 2.0 would not just turn off the lights. It would push our most advanced and dangerous technologies to the absolute limit of safety. The thin line separating modern civilization from a global humanitarian disaster would evaporate in a matter of weeks, proving that our technological advancement has come at the cost of extreme vulnerability. Emergency protocols designed for local and temporary disruptions would be completely inadequate for a planetary crisis. Governments would find themselves unable to coordinate relief efforts, distribute emergency supplies, or maintain public order as the structural pillars of society crumbled. The most dangerous misconception about a global solar storm is the belief that we could simply turn the power back on once the storm passes. In a typical blackout, the infrastructure remains intact. The power grid is simply shut down to protect itself. But a Carrington-level event does physical damage to the hardware of our electrical networks. Recovering from such an event would not be a matter of days or weeks. It would take years of slow, painful rebuilding. The core of the problem lies in our extra-high voltage transformers. These massive devices are the gatekeepers of the electrical grid, responsible for stepping up voltage for long-distance transmission and stepping it down for local distribution. When geomagnetically induced currents surge through the grid, they saturate the magnetic cores of these transformers, causing rapid overheating. The copper windings inside melt, and the insulating oil catches fire. Once an extra-high voltage transformer is destroyed, it cannot be repaired in the field. It must be completely replaced. Replacing these transformers is a logistical nightmare. They are not mass-produced items sitting in warehouses. Each extra-high voltage transformer is a custom-engineered machine, tailored to the specific electrical characteristics of its location. They are gargantuan structures, often weighing between 100 and 400 tons. Manufacturing a single transformer requires highly specialized raw materials, including high-grade electrical steel and copper, and takes between 12 and 24 months under normal economic conditions. Today, there are only a handful of factories worldwide capable of building these massive machines, and their production capacity is extremely limited. Furthermore, transporting a 400-ton transformer is an extraordinary engineering challenge. Under normal circumstances, they must be shipped via specialized rail cars and heavy-duty trucks, requiring months of planning, route clearance, and police escorts to navigate bridges and roads that can support their weight. In a post-blackout world where transportation networks have collapsed, fuel is scarce, and communication is non-existent. Moving these giant machines would be virtually impossible. The factories that build them would themselves be offline due to the lack of power, creating a circular trap. We need transformers to restore power, but we need power to build and transport transformers. This circular dependency would lead to a prolonged economic and social regression. Large regions of the developed world would remain without electricity for years. Without power, modern industries would collapse. Food production would drop to pre-industrial levels, and clean water would remain a luxury. Economists estimate that a Carrington Event 2.0 would cost the global economy trillions of dollars and could lead to a permanent decline in our standard of living. We would be forced to rebuild our civilization from the ground up, learning the hard way that our reliance on electricity was a single point of failure. The transition back to a stable society would be slow, marked by localized struggles for basic resources, and the realization that the world we once knew has been permanently altered by the fury of our own star. For the first time in history, humanity would experience a prolonged regression, a dark age defined not by a lack of knowledge, but by the physical destruction of the machines that powered our daily lives. Humanity is not entirely defenseless against the threat of extreme solar storms. Scientists and engineers around the world are actively working on ways to shield our technology from the next coronal mass ejection. The key to our survival lies in early warning systems and grid resilience. Our first line of defense is located in deep space. Satellites like the Deep Space Climate Observatory, positioned at the Lagrange point 1 between the Earth and the Sun, act as cosmic tripwires. They monitor the solar wind in real time, detecting the magnetic field and velocity of incoming plasma clouds. If a massive coronal mass ejection is heading our way, these space observatories can give us a warning of 15 to 60 minutes before the impact. While a 1-hour warning seems brief, it is long enough for grid operators to take preventive action. They can systematically shut down vulnerable parts of the network, isolate critical transformers, and decouple regional grids to prevent a cascading domino effect. By turning off the grid voluntarily, we can prevent the physical destruction of the hardware. Additionally, engineers are developing physical shields for the grid. This includes installing giant capacitor banks and neutral blockers at substations to stop geomagnetically induced currents from entering transformers. We are also building more resilient communication satellites that can withstand intense radiation. The cost of protecting our global infrastructure is high, but the cost of inaction is immeasurably higher. It is a race against time as the Sun operates on an 11-year solar cycle, and the probability of a Carrington-level event increases during solar maximum. Ultimately, the threat of extreme solar storms forces us to confront a profound truth about our species. We have built a civilization of incredible complexity, but we have built it on a foundation of electric current. We have connected the entire planet with copper wires and fiber optic cables, creating a global nervous system that is uniquely vulnerable to the magnetic whims of our star. The Sun is not a silent, peaceful light in the sky. It is a violent magnetic engine that can disrupt our lives at any moment. Our technological success has made us fragile, and our survival depends on our ability to respect the power of the cosmos. We must choose between investing in the protection of our global networks today or facing a future where our greatest achievements are erased in a matter of hours. The choice is ours, but the clock is ticking. As we look up at the Sun, we must remember that it is both the giver of life and the greatest threat to our modern way of existence. Preparing for this inevitable event is not a question of scientific curiosity. It is a matter of civilizational survival. The silent danger is out there, drifting toward us through the vacuum of space, waiting for the moment the magnetic lines reconnect. If a Carrington Event 2.0 hit tomorrow, how long do you think your local community could survive without the internet and power grid? Let me know your thoughts in the comments below.